Okay. So we were kind of discussing the digital fundamentals last week, and we will be continuing that. Probably this week, today and tomorrow, we might complete that digital basics, and then we will move to CMOS next week. That is a kind of plan. Uh, so let's continue where we left. Okay. So we have gone through the circuits. So which circuit this kind of, so ideally if you look at, right, say all this one, two, three, all of them are kind of, same, the functionality, but which one would you prefer? Okay. So when it comes to your PPA, okay, so I think I told you guys, so anything that we talk in the whole class, so I would be kind of more on PPA only. That is where the most of the learnings that you will see. So how do you optimize your power, and how do you optimize your performance, and how do you optimize your area, what are the different cells that you would use, and all of that. So our main focus would be on more on, focusing on the kind of, the PPA. Okay. And we have gone through the basic equations, the Boolean theorems, and then, solving some of them. So I gave, I think this two, or the one which I gave it as an assignment. Okay. Uh, so using De Morgan's theorem, you would be able to, optimize the circuit in a better way. Okay. And we also have discussed about the logical implementation using NAND, basically NAND and NAND implementation. Okay. And we were also, kind of talking about why. So we were also, kind of talking about, say, something called universal gates. Okay. So why, what are the gates that are called universal gates, and where do we use them, and, all of that. Okay. We were talking about like kind of NAND, NOR, and uh, MUX. So MUX is usually is not called as a universal gate, but we would be definitely, we can implement any kind of logic using MUX. Okay. So definitely we will treat MUX also a universal gate. Okay. Now this is a kind of problems that I posted in the group today. So implement the circuit using NAND. Okay. So you guys try it when you are having a free time. Okay. Now the next important topic is basically it's called Karnaugh maps. So see, it is, if you look at, right, it is end of the day humans, we are all human being, and you remembering all these formulas is not an easy thing, which you may use on day-to-day basis, you may not use on day-to-day basis, and definitely you won't even know any of this if you are in the PD domain. Okay. uh, because you are not the designer, and it is, and you are not developing the tool which would optimize the circuit and then, meet your PPA targets and etc. So to, if someone gives you any kind of, circuit, or say a functionality, now to solve that, it is always better if you use Karnaugh maps. And in college we would have learned Karnaugh maps up to four variables. Okay. Up to four variables. uh, I did up to five. Okay. So but that is and all, it's just, crazy thing. So if you know the basics, that should be okay. Now what is this Karnaugh map? Okay. So before that, now let's try to understand what are the different uh, numbering systems that we use in, say, in the designs. Okay. See, now there are two things that is kind of famous. One is binary. Okay. So which is going to be like kind of, say, 1011, something like this. Now say there is something called gray code. Okay. Now so What is the difference here? Anyone between these two?
Sir, in the gray code, we can have the only one bit change from one state to another state.
So in binary, if you look at between these two things, okay, and even if you look at these two things, so there are more than one bit changes. Okay, so there are more than one bit changes. Okay, more than one bit changes, which is basically going to consume a lot of power when you look at your overall power of your circuit. Now, so I as I said, right, like we would be talking about CMOS power dissipations, but to give you a just brief overview, I just wanted to take that. Say you have an inverter. Okay, now this is your just a simple inverter gate. Now this inverter is basically now implemented using CMOS logic, which is basically on the top it is PMOS, and then on the bottom it is NMOS. Okay, now so this is your I and say this is your Z. Okay, now if you look at here in this CMOS circuit, okay, so this is CMOS inverter. Okay, now in the CMOS circuit, so you have got totally kind of two different basic things. One is static power, okay, and second is dynamic power. Okay, now so in static we mainly call it all the leakages. Okay, all the leakages when the circuit is not in switching. Okay, when the circuit is basically not switching. And when it comes to dynamic, there are two cases. One is switching power, okay, and the other one is short circuit power. Okay, short circuit power. Now if you have a lot of switching, okay, see, when you have a circuit, it's basically the gates and the inputs are the kind of the values are kind of switching like this. Now your switching power would increase. Okay, so the basic formula for the switching power is, okay, alpha c v squared f. Okay, so this is basically switching activity. Okay, switching activity. Now remember, you being a PD engineer, right? Now, do we have any kind of thing that you can choose this? What kind of numbering system or what kind of the coding and that you are going to do it? Now, ideally, when your design is power critical, okay, when your design is power critical, so the architecture itself, so the RTL, so before that itself, architecture, okay, and then your RTL design comes into picture. So your architecture itself would decide what kind of numbering system that they are going to use. So now your RTL team would eventually take care of all such things. Okay, so now your switching power would increase if you use if you use binary as your basic thing, and people use gray code as one of the optimization or probably the implementation part, where your switching power would come down because, so in binary, as I said, right, like you have a more than one bit switching, whereas in case of gray you would just have only one bit. I'm just giving you uh, just random, I'm not really sure. Okay, so for example 1 0, so something like this it would come, and then 1 1 1 0, and then 1 1 0 0. So if you look at, right, between two states, you will see only one bit which is kind of changing. It's never the two bits. So in this case 0 is changing. Now in this case here it is changing. Now in this case it is kind of changing. Okay, so you should, the advantage of gray code is just that between two states there is only one bit which is kind of changing. Okay, and that is why we kind of prefer. Okay, now why I brought this here was your Karnaugh map uses gray code. Okay, so when we represent your Karnaugh map, or when you try to solve any kind of problem using Karnaugh map, so the Karnaugh map uses the gray code when it comes to the states. Any question here before I get into the slide? But one thing is that I would be explaining you guys in detail what is the meaning of switching power and what is the meaning of short circuit power, what are the different leakages that put together, called it as a static power and etc. So I just gave you a brief overview so that you understand what is the exactly meaning of power consumption and why you choosing this encoding, binary encoding or gray code encoding kind of things would actually bring down your power. Okay. Any questions?
So, KMap using gray code, the basic reason is the power optimization only.
No, it is basically it gives you optimized circuit. We will be talking about the thing is here, so we will just wait for a minute. But I just want if you guys have any kind of thing. So the basic thing is I need you to understand what is the meaning of multi-bit switching and what is the meaning of only one bit switching, and how your overall circuit, the overall power comes into picture. So that is where I'm just trying to relate. Karnap, we will try to discuss in depth.
Okay.
See, it gives you because I'll just wait for any other questions. Otherwise, I'll get started on the corner map. Okay. Now, so let's talk about corner maps. So now you have this is kind of one cell, two cell, three cell, and four cells. So the total number of cells are gonna be basically two to the power n, where n is number of variables. Okay, and here if you look at right, see you have a and b. Now two variables. So the first thing is going to be kind of A bar B bar and then A B bar and then A bar B. So it is basically ideally speaking, so it is going to be kind of 0 0 and then 0 1 and then this is going to be 1 0 and then this is going to be 1 1. Now, so if you look at as I said right, so between this cell and this cell there is going to be only one bit that is going to be different. Okay, so in terms of changes, right, see here 0 0 and here it is 1 0. Now if you look at between these two, it is kind of 0 0 and 0 1, but don't look at diagonally. That is not how it was designed. So it is now you look at between these two, so 0 1 and 1 1, only one bit which is kind of changing. Now here if you look at between these two, it is kind of only one bit that is kind of changing. Okay, now look at here. Say you have got your a b c three variables. Okay, now how are you going to construct this? So how many cells we need in total?
8 cells.
Okay, so you need 8 cells. Okay, now so this is what it is. Now how do we mark it? Say you take this as a and this is bc, so which is basically it is going to be say a bar and then a. Now what about here?
B bar C bar.
So it is going to be, let's do this, a decimal. Okay, so it is going to be, first state is going to be 1. So how many possible states here? 1, 2, 3, 4, 5, 6, 7. So 8 is going to be considered as a 0. Okay, so it is going to be, say, 0. Now 0 meaning it is going to be B bar and C bar. Now this is going to be 1. Now what would be the case here?
B bar C.
B bar
B
C.
bar
Okay,
B C bar.
now here, is it going to be
B
2
C.
or 3? Is it going to be 2 or 3? So now you need to understand
3.
between
3
these
sir.
2 things. Yeah, so it is
3,
going to be
sir.
3, it is going to be 2. Now in this case, it is going to be BC. And here,
B C bar.
No sir.
yeah,
B C bar that one.
yeah. Okay, now what would be the bottom ones? Can you guys tell me, the values?
4,
Okay,
4, 5,
4, 5,
5.
7, 6.
7, 6.
Okay, so now, so this is how you have to supposed to construct the things. So now the main thing why I covered the gray code was that is exactly what is used in the Karnaugh map to get the best optimized circuit. Now assuming, say, so in the case of 2 your output is 1. Okay, now say 4 the output is 1, and then say 6 the output is 1, and then say 7 the output is 1, the rest and all is kind of 0. So now how do you go on to fill this? So
Hello sir.
2, yes,
That is B C B bar C bar B bar C and that one is B C bar. No third cell. After that B C came. No?
you think that is not the thing. So your Karnaugh map is always something like this. So it is not the way you say. It is, as I told you, right, between the two states, it is always only one bit change. Okay. So now 2, where is the 2? So here it is, say, 1. Okay, and so 4, it is 1, and then 6 and 7. So there is a 1, 1. Okay, so now remember, so you have just constructed this K map. Now there is something called grouping. Okay, so the grouping goes 2 to the power n. So that means what? N is basically 2 to the power 3, which is going to be 8. So all the 8 cells, if all of them are 1, then you can actually club all of them to, group them and mark it as a 1. So that is the first thing. Now the next thing is 2 to the power 2. So now, if possible, you can group 4 cells. 8 cells can be grouped together first. That is a maximum possible in this scenario. And the second one is, so 4 cells can be grouped. If 8 cells are not possible, then try to group 4 cells. Okay. Okay. So just to make our life simple, right? So let's keep this also simple so that like we would have something. Okay. So now, and then 2 to the power 1, so it is going to be 2 cells, and then 2 to the power 0, which is going to be 1 cell. Okay, so now in this case, so is it possible 8 cells, is it possible to group all the 8 cells? Is it
No, sir.
to group all the 8 cells? So this is kind of say ruled out. Now what about here? 4 cells, is it possible?
Yes, sir.
Yes.
Yes, sir. Ward.
Okay, so you have 4 cells that can be grouped. Okay, now what is it going to be? 4 cells you have grouped. Now what is it going to be the outcome of this 4 grouping? So
B.
remember this A and A bar, it is gone. Okay, now C and C bar, that is actually gone. So here the outcome of this is just simple B. Okay, now so 2 cells, do we have anything?
Yes, sir.
Yes, sir, possible.
Okay, so now it is a kind of circular fashion. So you take a paper and you rotate it. Now join the both the edges. It will be like kind of circular. So the same thing. Now how it is possible? Now if you look at, so between this and between this there is only one bit that is kind of changing. So that is the reason you are able to group this particular cell and then this particular cell. So now what is it going to be outcome? So it is kind of A and then
AC bar.
so A C bar. Okay. So
AC bar.
now yeah. And then is there any cells that are left over here? There is nothing, right? So it's nothing is left over. So now for this functionality, for say if this is a given design, now the optimized circuit would be this. So now the first thing that you need to do is basically after this it is going to be easy, that AC bar C and then A and then say B. So this is the circuit. Okay, so now can we quickly summarize what is the steps that we followed? What is the first step? So when it comes to Karnaugh map, what is the first step? You need to get
First,
your
we need to check how
function.
many combinations we have that.
No, first thing is your functional detail. Okay, and then you need to bring your, what is this called? I have not written the whole truth table, but so write the truth table. Okay, that is always best thing, truth table. Okay, now next, draw k map. Okay, group the elements. Okay, and then I find final output equation. Final output equation, and then circuit. Draw the circuit. So this is the steps that I usually follow. Okay, now remember, this is the step that ideally if you follow, even if you make a mistake in these two things. Okay, so I'm talking about in terms of the entry level high interviews and etc. So if you follow the steps properly, instead of so you should, the interviewer should not get any kind of feeling that okay, you're kind of you came mugging up things and etc. So if you follow the process, so they will give you a hint whether it is right or wrong and things like that. So if you follow the process, that even if you give a wrong answer, there are chances that you would be kind of getting selected. Okay, so you should always define your process, what steps that you want will be following, irrespective of any kind of problem, and follow your steps. Okay, and that will help you to be more consistent. Okay, any question here on this particular K map or things?
So, if possible, can explain the what is the prime implicants, the essential prime implicants, the concepts in it came up.
Prime implicants in the K map. See, see, prime implicants, if you ask me, right? See, I always have kind of solved this kind of problems where they give you something like kind of, so there are the problem, right? So it is like kind of, say, sum of, say, zero, etc. And then plus don't care of certain things. Say this is going to be a functionality F. Okay. So this is how I always have solved the problems, but I'm not sure what kind of things that you're asking, Anjanelu.
Sir, and while grouping, we got that prime implicants, essential prime implicants. By grouping only, we can consider it, sir.
Okay, so how did I
Okay,
come
sir.
up with this B or something? Say when I group
By
4,
grouping, sir. By
yeah,
grouping card. Yeah, sir.
no, that's what we talked about it, no? So it is basically when you group 4 cells, say now in this case, so let's talk about the 4 cell grouping. Now, ideally speaking, so you have got A bar and then A, which is kind of covered in this 4. So that is not going to be valid at all. Now, here again, which is common. So only B is kind of common. So that is how we choose it. Okay. And when it comes to the 2 cells, right? So you are kind of taking where, this is these 2 cells, whereas your A is going to be common in both the cells. Now that is in terms of horizontal row. Now look at in terms of vertical. Now what is it common between these two? So it is a C bar is common. So that is how we actually group it. So this is how the K map is actually implemented. I'm not sure if I answered your question, but maybe I'll go back and check.
Hi, sir.
Yeah, hi.
Sir, actually, I mean, what I understood by the gray codes mapping with the K map. So, for this given input combinations, if my circuit is implemented, there will always be switching. I mean, there is only one set of device switching happening between the circuit.
Right.
But the
That
input changes, then there might be, you know,
No, see, I think the way we look at, right, I think it is like,
G.
uh, see, the inputs, right, it is, hey, there is a lot, some noise in the background. I think I did mute the person. Okay. See, if the input changes, that is automatically, you don't have any control, to be honest. But have you optimized your circuit in the best way that you can? That is a kind of question here. See, you don't have any kind of control on your inputs, okay? Because, see, end of the day, that would come from another circuit, ideally speaking, or say some kind of sensor data, ideally speaking, if you are kind of working on a say system, overall system perspective. So ideally speaking, right, so you may have a sensor data which is connected to A, another sensor data which is connected to B, and there could be another sensor which is connected to C. Now based on these three sensor data, this is what your system expects to generate the output. So you may not have any kind of control on the inputs, but when you kind of optimize your circuit, so you follow the schema and that would help you to come up with the best possible circuit, which would actually kind of take or say take less area, or say kind of better the cells, cell types, and etc.
Okay, sir. So basically, why I asked that question is as per the priorities that you said, like first three grouping, two grouping, in one grouping. So, I mean, I'm not sure. I just wanted to check with you. So, if I group it different way, like maybe twos, then is there any chance that other
That will
switching
see, it
combination?
is simple, right? Now let's do that. So since you are asking, right, let's do that. Now what you're saying is, now let's, what will happen if you try to, instead of group it four things together, right? Now try that out. No, let's do this. Say for example,
Okay.
now you're grouping these two. Now what is it going to be value?
This
Just
would
BC.
be, yeah,
Now you group these two,
BC bar,
PC bar, and then plus.
this one, yeah.
So A C bar. Now
Mhm.
ideally speaking, if you have to implement this circuit, now how many gates you ideally need?
One, two, three.
So ideally speaking, here in this case, there is a one inverter
Right.
and then one AND gate, and
one
then one OR gate. Okay.
right.
Now,
Right.
whereas in this case, it is going to be, as usual, one inverter and then three AND gate and then
Two OR
one,
gate.
no, one three input OR gate.
Okay. Yeah.
Okay. Assuming it's, I have all the kind of flexibility. I don't want to, go with the things extra. So
Understood.
now,
Yeah.
so this, ideally speaking, right, it's not going to help you in terms of PPA.
Okay.
So that is the reason I always say it's kind of priority is try to use, if you can, group all the 8 cells. Yes, you can actually, you would get the best optimized thing. Now, next, not possible. Okay, move to the next one like this.
Mhm.
So this is the order, but you cannot go randomly. That will not help you to optimize or achieve your the best circuit, if you ask me.
Yes, got it.
Okay, all right. So I'll give you a quick problem. Let's do it with four variable. So it's basically, so let us say f is equal to sum of, so 0, 1, 2, 3, and then 8, 9, 10, and 11, and then plus d. So that is something that don't care. You can say 12 and 13. It's something that don't care. Now, I'll give you a few minutes time. This is a class work. It is not your homework. This is a class work. I just want you to solve this and revert back with the answer. I'm also going to solve you as you do in parallel. Okay. Let's do this.
That's A, sir.
No, I think that you can just ignore it. So that you can construct. So you, what is the steps that we followed? So you just now try to create that and then do the things.
B bar, sir.
Okay.
Answer is B bar.
B bar, sir.
Okay.
B bar, please.
Okay. So now, so this is the for table ideally, if you ask me, correct? Or do you guys see something different?
It's the same, sir.
Yeah. So there are people with different answers. Do you guys want to revisit your answer?
Ashwin.
Okay. So now, ideally speaking, there is a 16 group since four variables, right? So 2 to the power 4, 16 cells, not possible. Now, so 2 to the power 3, it is going to be 8. Okay. Yes, it is possible. Okay. So if you put these two things, it is kind of 2 to the power 3. Basically, you can cover 8 cells together, and you don't need to worry about this don't use because it's of no use. uh, Sorry, don't care. Okay. Now your answer is going to be, so now in this case, the common thing, so here all are kind of covered, so there is nothing is going to be there in terms of C and D. and here between this and this, okay, so there is only B bar is common, so your F is going to be just B bar. So this is how you have to ideally implement. Now, yeah, I think hope you guys got an idea of how the KMAP works. uh, Devesh, I think there is something wrong with your answer, maybe the way you approached the problem.
So I consider don't care as well, sir.
Don't cares, you don't need to worry about it, because don't cares you can use it only when you really wanted to count them. Otherwise, you don't need to worry about the don't cares.
Okay, so if I mean, it would have been helping me to group with something which is getting missed, then I can consider. Otherwise, I leave it.
Exactly. So now let me give you a slight changes here in this. Now, say for example, in the same circuit, say for example, now say you have got these things. Okay. Now, if you look at right, say there is a chance of you having one four grouping here. Okay. Now there is a one more four grouping that is kind of like this also. Correct. But you know what? Because of this don't use, now what you can probably do here is you can actually group all these eight. Okay. So if you really wanted to make use of, if it is going to help you in terms of optimizing your circuit, then you can include them. Otherwise, I will not bother about them because they are anyway don't cares.
Okay.
Okay. So I think Hema, you also have somewhere something is kind of missed. Seems like you also have considered AC bar. Okay, so seems like you also have considered. Okay, this four. Okay, I got what you guys have done that. Okay, so I think yeah. So many people have kind of added this also this things. So common is going to be kind of, if you have to look at right, say plus say A C bar. I think this is what you guys have might have counted, because you have considered don't care also. So yeah, that's fine. But you don't need to worry about your don't cares. Okay. Yeah. Okay. All right. Okay. So that's on the K map. So before we move on to the next slide, we'll just you can take a look at one last thing on the K map. Okay, I think we'll move forward. Okay, so we'll just get into basics of combinational circuits. Okay, So probably what I would do is, let's just take a 5 minutes break. You guys go and take water or coffee or whatever you feel like, and then we will quickly get into these things. And so I'll just show you what I'm planning to cover today. So basic combinational circuits, and then how mux is, what is mux and how do we implement it, and try various styles of implementation using the mux, and then so logical implementation using mux, and then one more slide of given kind of say boolean equations, how do you implement that using mux. Okay. And then so with this we will try to wind up for the day. Okay, so we'll take 5 minutes break and then we can actually connect again. So it is 7:56, so let's just meet 8:05. Okay. Okay, so we have discussed the basic Boolean theorems and how what are the different ways of optimizing your circuit and all of that. Okay, now let's just go and try to learn basic blocks. I would say it's a kind of basic building blocks. Okay, so uh, so the whole circuits, right? So who the ICs, if you look at, right, so we would be doing lot of operations. So there could be arithmetic operations. It's like addition, subtraction, multiplication, and different operations that we would be doing it. Okay, because that is how the whole system is working. Okay, so now to do that, what are the basic things? So the thing is, one is basically the half adder. So now half adder is basically you'll have a two inputs. Okay, and then you will have one is basically sum, and another one is something called carry. Okay, now if you have to realize the circuit, then it is going to be kind of say sum. It is exactly, if you look at, looking at this, if you try to see which gate it is going to give you this, it is kind of XOR. Okay, and when it comes to carry, and when both the inputs are 1, okay, then your carry is going to be 1. So that means it's basically an AND. So now this is your half adder circuit. Okay, and now full adder. So what is the difference between half adder and a full adder? So in this case, half adder is just takes only two inputs without any kind of input carry, whereas when it comes to full adder, it takes your input carry as well. Okay, so your inputs both x and y, and then plus one more input, which is kind of say input carry. Now putting all these things together, okay, now what is your sum and what is your carry? So it is simple, right? Like as we said, right? Like, right? So when you have the even number of ones, so your carry is going to be kind of 1, and say here even number of ones. Okay, and even here also it is kind of 1. Okay, and here also it is kind of say more number of ones, and all the inputs are 1, so it is kind of 1. Okay, so now ideally speaking, you should actually use the same Karnaugh map method that we discussed just now, and then you can actually solve this. Okay, so here as usual, say there is a kind of XOR kind of thing, and then here it is kind of say XNOR kind of thing. But ideally you need to solve this circuit and then understand or probably come up with the circuit. So now this is your carry equation. Okay, and it is going to be this portion. Okay, and then your sum, it is basically x exclusive, basically x and y XOR, and then the output of that is again kind of XORed with your input carry. So this is how your basic building blocks are constructed. Okay. Now there are different adders. Ideally speaking, right now, how many bits we are doing it here? Any idea? How many bits we are actually doing it here?
3 bits, sir.
It is basically a one bit adder. Okay, it is just basically a one bit adder. So with three inputs, that is a basic thing. Okay. Now, if okay, so let me ask you this way. Now, if you are actually looking at faster system, okay, now what would be the adder that you would actually choose? Say, for example, okay, say for example, now that is just one bit adder. Say it's kind of say one bit full adder. So it is basically now if you have to mark this into a 4-bit adder, so it's simple, right? Now, how is our ALU is basically designed? So you guys know what is ALU, okay? Say this is kind of ALU. Say, let me do it this different way. So when it comes to ALU, right? Say for example, now this is actually say 4-bit. Okay, say A 4-bit. Okay. Now say this is B 4-bit. Okay. Now say this is your sum and then your carry, or say just see out or whatever it is. Now say this is ALU. Now how it is going to be designed ideally. So now what is that? You guys have to understand one thing, that always remember anything that goes into this ALU and the operation it is actually happens, right? We always add a registers. Remember, the value should not change when the operation is actually happening. You know what? We actually take this kind of circuit. Now, what we usually do is we actually say 4-bit registers. 4-bit registers. Okay. Now, after that, even your sum would be kind of 4-bit registers, or say it would be more actually 4 plus bit registers. So it is always clocked. Remember, when you design a system, you might have gone through your basic digitals and everything, but ideally when you actually the way the each and every circuit that would be done is there is a 4-bit registers. You load the data parallel in parallel out. Okay. Now control it with the clock. Okay. Now control it with the clock. Okay. And then you pass the data, because when the ALU is actually doing its operation, it could be your addition, subtraction, or whatever it is. Now that would actually kind of, if the input is continuously changing, right, then it would be kind of giving you wrong values. So we add registers before it is going to the ALU, and then after the operation again there would be a outputs that would be maintained. Okay. So now in this case, right, say it is a 4-bit ALU. Now there would be a registers. Basically, it's kind of say 4-bit full adders. Say this is x1, y1. Okay. Now say s1. Now the c0. Okay. Now from here it is going here. So now, ideally speaking, right, what is the best way that you can? So is this best thing that you would design if you are looking for a faster system?
No.
Then what would you do?
Parallel connection.
But how do you calculate your carry? See, now ideally, if you ask me, right, there is a concept called critical path in the VLSI in our timing. So we call something called critical path. Okay. Now, what is this critical path meaning? If you look at, right, anything that is more in terms of higher delay and which is kind of going to hit your performance. Okay, so it is something that we call it as a critical path. Now, in this case, the whole critical path is x and y is not at all a critical because they can be calculated. But now the C in, okay, this is the critical path. Okay, so now if you look at, right, there are different types of adders. Okay, so different types of adders. So if you look at what is this adder is called, can anyone tell me what kind of adder it is?
Triple
Triple carry adder.
Yeah, exactly. So this is a ripple carry adder. Okay, now what are the other adders that you know? So one is carry look ahead adder. Okay, and then there is something called carry save adder. Carry save adder. So there are different architectures to mitigate your risk. Okay, so the way you construct the 4-bit adder or 8-bit adders and all, so you should know what is the time it is going to take. Okay, and is it going to meet my frequency targets in the design that I have, and all of that. So the reason is, ideally, why I'm covering all this is, when the moment you start your PD activities, physical design activities, you will never see them into in the form of functionality. That is the biggest problem with the PD engineers. Okay, because it is just end of the day, it is kind of ridge to ridge path and a combo logic, and that is how they always talk. But if you are actually kind of good in this basics, you can actually, by looking at the circuit, you can actually go and give a feedback to your RTL designers. That is where your value addition comes into picture. Okay, so it is always you should know the basics and looking at your critical path that you would learn little later, and then you should actually kind of working with your RTL design team and then make your life easier. That is how I look at. So now coming back to our topic, so there are different types of adders. So just check what is what and how they are different from each other and etc. That would actually help you. And then this is going to be say kind of next week thing. So I want you to design a say 8-bit ALU. Okay, 8-bit ALU. That is going to be a homework for the next whole week. So now when I have a control say AB. Okay, now when 00 is my input, so that means the ALU should do addition. Okay, when it is 0 and 1, say this kind of subtraction. Okay, and then 1 0 multiplication. Okay, now 1 1 say shift left. Okay, so or say you can say even kind of one's complement. Okay, so I want you to learn how to design a simple ALU so that you understand what is what, and then uh, you know from a system perspective you will have an idea. Okay. Okay, moving on. So we are done with off adders and full adder, and we also have discussed about 4-bit adders and etc. Now the next important thing that we would be looking at is there is something called multiplexer. Okay, so what is this mux? Many inputs and one output. Now you have, how do you now decide which input should go to actually the output? So that is something that we call it as a select line. Okay, so now the real practical example, right now, say you have a kind of railway station. Okay, so now look at this. So you have got multiple kind of platforms. Now the controller would decide, okay, if this train has to go first, or say this train has to go first. Now he controls the whole tracks. Okay, and this is exactly what we do with the mux in our designs. Okay, okay. Now a mux is a digital switch that has multiple inputs and then and a single output, and the select line determines which input is routed to the output. Okay, now if you look at, right, the number of inputs, it is always 2 to the power n. Okay, the number of inputs are always going to be kind of say 2 to the power n. So that is how we call it, like kind of always say 2 cross 1 mux, or 4 cross 1 mux. Okay, or 8 cross 1, or 16 cross 1. Okay, now where this kind of things are going to be used in real thing.
Encoders and decoders.
Exactly. So there you may have multiple inputs, and they might wanted to a kind of say parallel to serial conversion kind of things, places they might be used. Now let's try to understand a little more in detail what it is. Okay, now 2 cross 1 mux. So what is this meaning of 2 cross 1 mux? So there is a B, and then say yes, and then say Z. Okay, now when yes is 0, what is your output? Your output is going to be A. So
Yeah.
0 and then 1. So now when S is 1, it is going to be B. Okay, so now this is how your mux actually operates. Now what is the formula for this? So Z equal to yes bar
S bar
S
A.
bar A, SP.
and then yes B. Okay, now remember, you might have seen in your books and all, say this kind of dabba, say they just say two inputs and just say they mux. But ideally when you get into industry you will see something always like this. So any kind of circuits, the diagrams, the design diagrams and circuits and anything that you see, it is going to be something like this always. So remember, this is how it is represent, the mux are represented in the real industry. Okay, now so this is kind of a diagram, mux diagram, but internal circuit is going to be kind of 2 AND gates, and the output of them are kind of say odd, and then say this is A, and say this is yes, and then this is B. So this is your mux diagram, the internal diagram. Okay. Now, so let's talk about quickly on the 4x1 mux. Now look at here. You have got two control inputs and then four inputs. So what is this meaning is the number of in control inputs and the that is actually kind of decides the number of inputs. Say this is going to be kind of 2 to 3 power n, and this is going to be kind of say n number of control inputs. Okay, control inputs, n number of control inputs. Now say two control inputs, that means here 2 to the power 2, which is going to be 4 inputs. Okay, that is how your mux is basically kind of the design. Now in this case, remember, so I always say I0, I1, I2, I3, and then so this is going to be say S1 or say S0 and S1, and then say this is basically Z. Now in this case, your what is going to be your truth table? So S1 and S0. So S1 and S0. So it is going to be when it is 0, 1, 2, 3. So this is going to be 0, 0, 0, 1, and 1, 0, 1, 1. Now, what is going to be your outputs in case of 1? In case of basically the first case,
I naught,
I naught and
I1,
I1, and then I2, and then I3. Okay, so this is how it is actually designed. Now, so see, you have got your 4x1 mux here, right? Now, I have only 2x1 mux. I don't have 4x1 mux, but I need 4x1. Now, how would you design that using only 2x1? How do you design only, how do you design 4x1 using only 2x1?
By using 3 2x1 mux.
Okay, how?
For out of the 4 input for 2x1 mux, 2 input is for the 1 mux, and another 2 input is for another 1 mux. The
So,
2
what you're
outputs will be
saying
given to
is,
the
Like
other.
I0, I1 in the first mux, and then I2, I3 for the second
Yeah.
mux, and then select
okay,
lines will be
The
reversed.
output of these two will be third one.
so it is going to be I2 and then you're telling I3. Okay, now what about your control lines?
Common, only one control line, sir.
Okay, so it is, you
Common
are
for
saying
both
it is
mux.
common. Okay, yeah, that is going to be S0 or S1.
Yes, sir.
Which
LSB
one?
will be given to the first stage of mux.
Okay, so it is basically what you're saying is S0. Is that right?
Yes, sir.
Okay, now this, how it is going to be?
So outputs will go to this mux, and then bar should go.
Okay, now what about this collect line here?
S1,
S1.
sir.
Yes,
S1.
one. Okay, so now you guys, I don't know, I have not at all analyzed it. Now, how do you analyze this? So I just followed you guys, whatever you were telling. Okay, now, how do you verify that, it is actually as per this truth table? How do you verify this? Whether this circuit and this truth table, are they in sync or no? How do you verify that?
So we need to analyze by placing S1 S naught as 0, 0, so that we get I naught there as
Okay,
output.
so now what you're saying is, say S0 is basically 0, and then S1 is also 0. Now, what is your Z in this case?
As truth table, we are supposed to get I naught. So if we check the circuit, if we get the same, then
Okay,
we design correctly.
okay, so now in this case, you will get this is going to be kind of I0 will come over here and I2 will come over here, correct? Because 0, 0,
Yes, sir.
correct? And then now this is going to be coming over here. Now these two, again 0. So here I naught is going to come out. Okay. Now, okay, I agree. Now say S0, 1. Okay. Or S1 is equal to 0. Now what is going to be Z?
I2, sir. Sorry, I1, sir.
So S01 meaning it is basically I1, and then I3 comes over here, and S1 is basically 0. So it is going to be kind of I1. Okay. Now S0 is basically 0 now, and then S1 is 1. Now what is it going to be?
I2.
Okay, got it. So now ideally speaking, this circuit is same as this. It is actually this truth table, and then this circuit is are in sync. Correct? Now, there are written tests where you would come across, we would just simply go and ask to implement 16 cross 1 mux. Okay? How many 2 cross 1 you need? How many 2 cross 1 mux you need? I have only 2 cross 1 mux.
15, sir.
Okay, so what is the thumb rule that you are following here?
By dividing with 2, 16 by 2, and remainder again with 2, like that.
It is simple n minus 1. Your n is basically nothing but your 16. And then if you have to implement 16 cross 1 using 2 cross 1, you need 15. So that is the rule that I actually follow. Okay. So when it comes to your 2 cross 1 based implementation, so this is how I actually have. I see it's individuals will have a different way of dealing things or working out things. But in this case, I just follow, say just 16, okay, minus 1. So 15 muxes I need. It is just even a second answers that we would just do it. And now let's say if you have to implement this 8 cross 1 using this, how many you need?
7, sir.
Yeah. So you need totally 7 2 cross 1 mux you need to implement 8 cross 1 mux. Okay. Okay. All right. Uh, now, so we were talking about mux being universal gate, correct? Now, can you guys quickly design, say basically uh, implement using mux? Okay, so my request is, say I need an inverter, but I don't have an inverter with me. I have only mux with me. Now design basically implement an inverter using mux, and then buffer, and then AND gate, and then say OR gate. Can we quickly do this? So in this case, I have got 2x1 mux. Now how do we implement it? So you got here, say select line is going to be a compulsory thing. So now inverter. So say this is your I, this is your Z. Now what you will connect where?
Input at the selection line. A at the selection line.
There is only I don't know what here are you talking about. So
I.
this is I0 and say I1. Say this is kind of, say this select line is now connected to your I. Correct?
Yeah.
Okay. So now what else? That alone is sufficient?
I not equal to 1.
Okay.
I
I
1
not
0.
equal to, okay. So basically what you're saying is you have to give this I naught to is 1 and this is going to be 0.
0.
Okay. Now, so this is going to work as an inverter.
Sorry. I not
Okay.
equal to I bar. Sorry.
No, you don't need to struggle so much. You can just go ahead with
Okay.
this. It is going to work. Okay. So it is simple, right? When you give I 0, now what is it going to come out? 1 is going to be your output.
1.
Okay. Now when I is equal to 1, what is it going to be your output? 0.
0.
Okay. Now, so this is your inverter. So you are able to design an inverter using the mux. Now, what about your buffer?
Just inverting will do, sir. Like I0 to 0 and I1.
Okay. So what you are saying is basically, say this is 1, inverting meaning 0,
Yeah, right.
and this is 1, and then what you are saying is here, it is basically I.
Correct.
Okay. All right. Now, what about AND gate?
I0 need to connect it with 0 and I1 is connected with A and select line as B.
Okay. So your AND is going to be, say the way I would always prefer is you having your truth table and all of that. So you eventually have to work it out that way. The process that I talked about it. Okay. Now, so this is, see, remember one thing, the way we always do it, right? One input has to be always, select line should be always your one of your input. Okay. So let's take A. Okay. And then when this is, what is it going to be? When A is 0, what will be your output?
0, sir.
0.
Okay. So now A, B, Z, 0, 0, 0, 1, 1, 0, 1, 1, now 0, 0, 0, 1. Okay. Now, so when A is 0, so your output is basically 0. So you have taken care. Now, when A is 1, what it is?
B, sir.
B.
Because the other thing is exactly following the B. Okay, so your other input, you can just name it as just simply B. Okay, so now this is going to work as exactly the AND gate. Okay, and what about OR? See, it is always good if you can draw the truth table and figure out how you are analyzing things. Okay, so you can take this as a homework. The remaining one, say, I want you to try NAND and NOR and then so OR. Okay, so these things you can try it in home. Okay, because I wanted to close the remaining slides. Okay, otherwise we will be continuously extending this, which is gonna delay our whole progress. Okay, so this particular slide, see now, this is the equation that I wanted to implement using MUX. Okay, now what is the basic thing that we do? What is the process that we follow? Get your truth table.
And optimizing using K-maps.
Okay, so truth table. Now in this case, we are not actually going ahead with that way, but you got your truth table. Okay, now you know in which conditions they are kind of one. Now you are going to implement this using, say, how many variables we have here?
4, sir.
4 variables, but
Hmm.
remember you can actually use 3 variables as a control lines. Okay, 3 variables as a control lines, and one you can use it as a one of the inputs. Okay, one you can use it as a one of the inputs. So now having said this, now you know what, you wanted to implement this whole function using a 8 cross 1 mux. Okay, using a 8 cross 1 mux. Okay, now so you have done this truth table. Now to implement using this mux, what I want you to do is say z dash, basically z bar and z. Okay, now just write it. So 0, 1, 2, 3, and etc. Now I0, I1, so I0, I1, all the inputs on the top, and here the input that is not used as a select line. Now that is actually kind of say z bar and z. Okay, now just this is just simple, right? It's 0, 1, 2, 3, 4, 5. Mark it as it is. So it is just this boolean, the normal uh, decimal, number. Okay, now wherever there are ones, now here there is a 1. Okay, so this is 0, 1, 2. Just round it. Okay, now next 3, 4, round it. Okay, so now just go ahead and mark all the numbers that are kind of having output 1. Now after your rounding, you know what next? If both of them are not having round, then just substitute 0. Now if both of them are having rounds, connect them as a 1. Now only one it is rounded. Now whatever that is round, so which is basically z bar. Okay, use that to connect. Okay, now in this case it is 0 because both of them are not kind of rounded, and then this is z bar. Okay, because only on the top it is there, and then this is 0. Okay, now you have got I0, what is the value? I1 z bar, I2 z bar, I3 z bar. Now ideally speaking, I would just say 0 z bar. Okay, Now I4 is basically 1, and then I5 is 0, I6 is Z bar, and this guy is 0. Now this is going to be W, X, and Y. Now if you try to check this, you will actually have 0. Basically this the whole this mux whatever that you have connected here, it is going to the output of mux is going to have this as a functionality. So this is another way which you may know or may not know. uh, okay, and it is very simple to implement as well, any kind of logic. So but for this, as I said, right, you need to know writing a truth table, pick the right mux. Okay, it is always n minus 1 variables. Okay, that basically becomes a control line, and then choose that those many control lines as a the mux which is having those many control lines, that is basically 8 cross 1, and then all the inputs now you need to connect using certain elements. Basically you are going to connect it in the form of 0 and 1, Z or Z bar. So that is exactly, now how do you get that? Using this particular method. Any question here?
It's a kind of another
Sir,
way of K-map.
You can say that way, yeah. So this, see, there are different methods. So this is one of the method that I found it easier.
Sir, is it possible to change the variables instead of taking the WXY as the control lines? If we take the XY Z as a controller and then W as a common one, what will happen? Whether it is work same or different time?
You have to change your numbers here accordingly.
Oh, in the table. Okay, okay.
Yes. See, your Z0. So when it look at 0, right? So it is, this two are the one which is, when all of them are 0, these two, the basically I0 is going to come out, correct? So now how
Yeah,
are
yes,
you
sir.
taking care of that? So you can change, you can pick the control line, whatever that you want, but accordingly, this table numbers would change. So maybe instead of 0 and 1 here, it might be 0, 1, it may be a different number, or maybe 0 and so this now this table would change, and accordingly the markings would change, and then your final values would change.
Okay, thank you, sir.
Yeah.
sir, here we implementing 4 variable function using 3 select lines, right? Right.
Correct.
So here we taking a Z bar and Z at the implementation table.
Is
So
that
if you
basically
want to,
one of the input you are taking it, assuming you have a
yes,
inverting signal also available.
okay, sir. So if you want to implement this using 4:1 mux, we can use instead of Z bar and Z, we take Y and Z there. Y bar, Z bar, Y, Z bar, like that, for
uh
combinations.
i I think it should be okay, but maybe I'm not really sure. I need to solve and check, Sri Lakshmi.
Okay, sir.
No, see, once you know the method, right, then all it is just a matter of time for you to try to apply the values and check, right?
Yes, sir.
Now, see, in this case, right, you wanted to do something on this. Now, take this, no? So simple, right? See, you take this as a first 4 cross 1 mux, and this is another 4 cross 1 mux, and use two W and X. Now, you need to say it is going to be simple, right? Say, what you are saying is,
No, sir. Using only single 4:1 mux. And here as input we take single variable, right? Z variable. Instead of Z variable, can we take 2 variables in input?
okay, what you are asking is basically, can I use Y, X and Y, basically Y and Z as an input variable?
Yes, sir, exactly.
So I don't think so. It is not possible. So you may not have the combinations getting you the right outputs. You
Okay,
may
sir.
not have it likely. Maybe I'll have to refer some books and see whether it is really going to be possible or not. But I think that should be okay. You don't need to struggle so much. See, when they are giving you four variable, obviously you need three control lines. You cannot do it with only two lines, if you ask me. That is how I look at always.
Okay, sir.
Okay. Yeah. Okay. So I think that's all on the combinational. So now, so there are certain homeworks. Okay. So I want you guys to just don't need to solve, and you're not preparing for any exams. Just understand procedures, and that would actually help you uh, to have solid understanding. Okay. So just go through what is mux, demux, and then decoder, encoder, priority encoders, and then we discussed about off adder and full adder, and then 4-bit adders. So let's say if I wanted to use, say I wanted to hit 2 gigahertz frequency now, which would be the adder that you would suggest? Okay, so just try to spend some time and try to look at what is the critical path, and I'm not worried about power here. Say for example, I just give you a simple problem. Say for example, I'm going to work in 2 gigahertz design. Okay, now I need to choose the right adder so that I can hit the 2 gigahertz, and I'm not worried about power in this case because my frequency is higher preference or higher, high priority. So now, which adder would actually help me among all this? Or there could be different, more adder as well. So take a look at all that and spend some time and see. The reason why I'm trying to cover all this is, as I told you, right, there are designs who are see, look at this way, there are freshers in everywhere. Okay, so there are people with good amount of knowledge in design as well, or there are people kind of new to the whole design, and he is writing a code, but it is actually screwing up your implementation. So always think that, don't trust the guy who's any kind of things that, okay, whether he's an expert on things. You do what you are supposed to do. Question and ask for more clarity, or ask for clarifications, call for a meeting. So that is how I usually do it. So that actually helps me creating a rapport between me and my designer, and then he understands that, okay, if he doesn't do good job, he knows that I'm going to get back to him. Okay, so it is always makes your life easier. Okay, so that is why I'm just trying to spend some time on all this and look at what are the different multipliers. So there is a Booth's algorithm that I have implemented when I was actually in the early days of my career, and etc. And then you have a comparator, and then code converters. Okay, so just have a look at all this. As I'm repeating again, you are not giving any exams. Just go through it for your knowledge. Okay, and here for your information, we are not going to get into any kind of exam pattern here. It is a more of learn to make yourself better. Okay, so that is how I always say, and we are not interested in solving any equations, and you don't need to mug up any kind of formulas and all of that. So just understand how the concept, how the logic works, and what is the concept behind that is good enough. Okay. Okay, I think that's all for the day. I think we are on time. So what we will be doing tomorrow is, I will be just talking about sequential circuits. We will be talking about solving some problems, and we will be looking at different registers and what is the meaning of universal registers, and we'll be talking about excitation table, and we will try to implement few counters and etc. And we will also just go through what is FSM, but we will not be spending too much time on it. Okay, so that is going to be the tomorrow's topic. So I hope tomorrow we will wind up the whole digital part. That is a goal that I have. Okay. Okay. All right, guys. See you tomorrow. Take care. If you have any questions, I will be here. I'm here to answer you. If not, then we are done. Okay, see you guys then. Bye.
Thank you, sir.
Thank you.